Welcome to The Explainer. I'm Dr. Cam, and today we're stepping right into the breathtaking, microscopic universe of analytical chemistry. Imagine a world where the hidden, invisible components of a complex mixture can be elegantly and rapidly pulled apart right before your very eyes. That's exactly what we're diving into today as we explore the visually stunning realm of thin layer chromatography. It's an essential, highly versatile technique that honestly stands as a fundamental pillar of scientific discovery and analysis.
Now you might be wondering, how do scientists instantly know the exact chemical makeup of a really complex mixture? Think about it. Whether it's a forensic investigator analyzing a mysterious powder at a crime scene, or maybe a food chemist verifying the absolute purity of a botanical extract, they need a method that is incredibly fast and completely reliable. The ultimate analytical solution to this kind of real-world mystery is thin layer chromatography. It lets us illuminate that hidden chemical architecture so we can see exactly what molecules are hiding within.
So, here's our roadmap for today. We're going to cover unlocking chemical secrets, the core principle, step-by-step procedure, visualizing the invisible, and finally, real-world applications.
Let's kick things off with Section 1, Unlocking Chemical Secrets.
So, what exactly is thin layer chromatography, or TLC for short? Well, it's a fast, highly versatile planar chromatographic method. Its main job is to separate non-volatile mixtures into their individual pure components, and it pulls off this microscopic ballet by using two key things, a stationary phase and a mobile phase. What's truly incredible about TLC, though, is its sheer efficiency. A scientist can work with literally micrograms of material to decode a compound's identity and purity. It's an absolute powerhouse of analysis, all happening right there on a tiny glass plate.
Moving right along to Section 2, the core principle.
To really understand how these molecules actually separate from one another, let's use a simple analogy. Think of the molecules in our sample as runners in a race, and they're dealing with two main opposing forces. First up, we've got the stationary phase, which you can think of as the terrain. It's a thin, uniform layer of an adsorbent material, usually something like silica gel or alumina that's coated onto a backing of glass, aluminum, or plastic. This terrain inherently tries to hold those runners back. On the flip side, we have the mobile phase, which acts a lot like the wind pushing the runners forward. This is a liquid solvent, or maybe a mixture of solvents, that gets drawn up the plate via capillary action. So the molecules are constantly caught in this tug-of-war, being pulled between the stationary terrain holding them down and the mobile wind pushing them up. And because of that tug-of-war, compounds separate based on their own unique affinities. If a particular molecule has a really strong attraction or affinity to the stationary terrain, it's going to move very slowly. But if it favors that mobile wind, it travels much further up the plate. Since every single unique chemical component interacts differently with these two phases, they travel at completely different rates. And that's how they neatly separate out into those distinct, colorful spots.
That brings us to Section 3, Step-by-Step Procedure.
Now, TLC is a highly precise four-part process that demands some serious laboratory precision. The sequence is 1. Prepare the chamber and plate, 2. Spot the sample, 3. Develop the plate, and 4. Visualize the separated spots. Proper preparation here is absolutely critical, especially making sure you saturate the chamber with solvent vapors. That creates this perfect equilibrium to avoid what we call edge effects, ensuring our solvent front advances perfectly straight. It's just a thrilling example of the rigorous scientific method in action. Let's zoom in on that spotting process. A tiny, highly concentrated amount of our sample mixture is very carefully deposited onto a lightly penciled origin line right near the base of the plate. To pull this off, chemists use a microscopic, hand-drawn glass capillary tube. They literally draw it out over heat until it's thinner than a needle. This allows for a microscopic, super precise transfer of just a trace of the sample, which keeps that starting spot as tight as possible so we get a really crisp separation later on.
Next up, we prep the development chamber. We place a small pool of our solvent, that's the mobile phase, at the bottom of a sealed container. Now, here is a critical detail, guys. The level of the mobile phase must be below the penciled line where we spotted our sample. If the solvent level is even a little too high, our precious sample compounds will just wash away and dissolve straight into the solvent pool at the bottom. The entire experiment would be ruined. So it's a very delicate, high-stakes balance. And here is where we get that elegant progression of the plate developing. We place the spotted plate into the closed chamber, and slowly, silently, the solvent begins its ascent. It's drawn upwards entirely by capillary action, fighting right against gravity. As that solvent front moves up, it carries our separated compounds right along with it. But you have to watch this like a hawk. You must pull the plate from the chamber before the solvent front runs completely off the top edge. If you don't, all that beautifully separated data just becomes completely unreadable.
Okay, Section 4, Visualizing the Invisible.
Before we can actually reveal these invisible compounds, we need to know how to measure what we're about to see. We use this powerful mathematical tool called the retention factor, or simply the RF value. It's a dimensionless ratio. You just calculate the distance traveled by a specific compound, and you divide it by the total distance traveled by the solvent front. It's that simple. And under controlled conditions, this RF value is incredibly consistent. It acts as a unique numerical fingerprint, giving us a way to collaboratively discover and identify totally unknown substances just by comparing their RF values to known chemical standards.
Now, get ready for something truly spectacular. One of the absolute best ways to see these colorless compounds is by hitting them with ultraviolet light. You see, many TLC plates are manufactured with just a tiny amount of a fluorescent compound mixed right into the silica gel. So, when you shine a UV blacklight onto the plate, the whole background glows brightly. But if one of our separated compounds happens to absorb that UV light, it casts a stark, dark shadow, instantly revealing its hidden location on the plate. It's like magic, but it's science.
But what happens if our compounds don't react to UV light? Well, that's where chemical staining reagents jump in to save the day. By dipping or spraying the dried plate with specific chemicals, we can trigger a reaction that creates a visible color. And the cool part is, different stains selectively target very specific molecular classes. For instance, if you're hunting for amino acids, you'd spray the plate with 9-hydrin, heat it up a bit, and watch those invisible spots turn a deep, vibrant purple. Or, iodine vapors can temporarily turn general organics a yellowish brown, while potassium permanganate brilliantly reveals oxidizable groups without even needing any heat. It is literally chemistry revealing chemistry.
Finally, let's look at Section 5, Real-World Applications.
The sheer versatility of thin layer chromatography is pretty astounding when you realize how many industries it impacts. It's heavily relied upon in environmental science for identifying dangerous pollutants and pesticides lurking in our water and soil. In the pharmaceutical industry, it is absolutely vital for quality control, verifying the purity of life-saving medications. Forensic scientists swear by it to analyze the exact dye composition of microscopic fibers found at crime scenes. Food scientists even use TLC to sniff out adulterated honey and bee products. And of course, organic chemists use it constantly to monitor the real-time progress of really complex synthetic reactions. It's a true frontline tool for safety, discovery, and justice.
So as we wrap up today's explainer, I want to leave you with one final provocative thought. Think about the medications you take, the food you eat, the clothes you wear, and the whole environment around you. What hidden mixtures do you interact with every single day that thin layer chromatography could decode? The chemistry of our world is endlessly complex, but with ingenious tools like TLC, the invisible almost always comes to light. Keep questioning and keep exploring.